Good evening, everyone, and today we're going to be looking at the divisibility rule by 11. So the rule, if you're not familiar with it, let's say you have a number that is A, B, C, D, E, then if A plus B, sorry, I've already got it wrong, that's great. A minus B plus C minus D plus E is equal to 0, then the number is a multiple of 11. So quite simple, less simple to prove. So we're going to start with a base case of our number is A, B, C, D, E. So our number is A, B, C, D, E. That is equal to E plus 10D, this is familiar ground still, plus 100C plus 1000B plus 10,000A. Still familiar territory. So A, B, C, D, E is equal to 11D, so I had a moment to think there, 11D plus 99C plus 1001B plus 9,999A. Now note that these are all multiples of 11, but they're all plus or minus 1 from a multiple of 10. That's going to be important when we're proving for the general case. Plus E, because we haven't listed an E here. Minus D to get to our 10Ds. Plus C to get to our 100Cs. Minus B plus A. Now, in this case, it's relatively easy to see. This is a multiple of 11, and it's this expression here, what we were looking for earlier. If that is a multiple of 11, then the entire number is a multiple of 11. Therefore, A, B, C, D, E will be a multiple of 11. So that's the easier example. Now to the more complicated bit. What I need to prove is for any number, so going on into the billions to the trillions, however large it gets, you will always be able to get plus or minus 1 from a multiple of 10, and therefore that will always be plus or minus 1 from a multiple of 11. Which means that we will be able to extricate this expression from it. So what we're going to do is we're going to prove by induction that 10 to the n is identical to minus 1 to the n mod 11. Right, so that's what we're going to try and prove. So here's our aim. That's what we're trying to prove. Okay, so try n equals 0 to start with. So 10 to the 0 is equal to 1. So therefore, and 1 is equal to 1 mod 11, and 1 is equal to minus 1 to the 0, minus 1 to the 0 is just 1 mod 11. So true for n equal to 0. Let's try n equals 1 as well, just in case it's different. So for n equals 1, 10 to the 1 is equal to 10. 10 is equal to minus 1 mod 11, and 10 is therefore equal to minus 1 to the 1 mod 11. Minus 1 to the 1 is just minus 1, so true for n equal to 1. I'm going to assume true for n equals k. I just like k, that's why I'm using k. So we have that, let's look at our expression. So 10 to the k is equal to, the expression we're assuming true is that 10 to the k is equal to minus 1 to the k mod 11. And we're going to try n equals k plus 1. Right, so 10 to the k plus 1 is equal to 10 to the k times 10 to the 1, because the indices add if you multiply the two numbers. So, and 10 to the k times 10 to the 1 is equal to, from our expression up here, minus 1 to the k mod 11 times minus 1 to the 1 mod 11, which is equal to, so 10 to the k plus 1 is equal to minus 1 to the k plus 1 mod 11, because what we had here is minus 1 to the k mod 11. So we've got if k, let's say k was even, we've got 1 greater than a multiple of 11 times by 1 less than a multiple of 11. Therefore, it's just going to be a multiple of 11. Or, actually no, that's not necessarily true. But the point is, you can add the powers here. So you're left with 10 to the k plus 1 is equal to minus 1 to the k plus 1 mod 11, which is what we were looking for. So that's fine. So we say, conclusionary statement, true for, and then we can get back to our original proof. True for n equals 0, n equals 1. True for n equals k, which implies true for n equals k plus 1. Therefore, true for all, there's our symbol, for all n belonging to the, I'm going to say positive integers, because I haven't said anything but positive integers, and 0. So maybe plus 0, question mark, because is 0 an integer? Is 0 a positive integer? I think, no, it's not. So I'm just going to say and 0. Okay. So getting back to our proof, we're going to do a number ak and so ever many digits, a2, a1, a0. That's our number. And that's going to be a0 plus 10 a1 plus 100, if I can actually write, 100 a2 plus all the way 2 plus 10 to the k ak. Right, so all familiar so far. Then we've got ak a0 all the way to a0 is equal to, this is where that thing we've just proved comes in, 11 times. Now remember how it's always going to be plus or minus the next multiple of 11. So it's going to be 11 times something, but for each power of 10, it's either going to be plus 1 mod 11 or minus 1 mod 11, which means we're going to be left with plus or minus, plus minus a0 plus a0 minus a1 plus a2 minus all the way to, and I'm going to assume plus ak, because it's either an even or odd k, and therefore it will either be a plus 1 or a minus 1. So you've got your plus minus here to reflect the fact that it could be either way around. That's to reflect the evenness. Sorry. And basically we've got a multiple of 11 here, and if the expression we have here is a multiple of 11, then our whole number is a multiple of 11. So we can say if this, actually no, we can just say if sum of even minus sum of odd order digits. So the even odd order digits are the a0, a2. So I'll say i.e. a0, A2, etc., i.e. A1, A3. So if that minus that is equal to 0, then number is a multiple of 11. Multiple of 11. Thank you for attending this video, and I look forward to see you next time. Oh, wow, that was a long effort. Well, tomorrow then, or some point next week.